Hello, we are Team Tensorix, Team ID 80067, and our problem statement is 25071, AI-based rockfall prediction and alert system for open pit mines. Rockfalls kill hundreds each year, and India's open pit mines remain highly vulnerable. A single generic model won't work because geological conditions differ across India. That's why we propose a scalable pipeline tailored to mine specific conditions. Supervisors can access real time dashboards with safety alerts and suggestions, while miners receive SMS or WhatsApp alerts to keep them safe on the ground. Moving to our novel features, we use explainable AI with SHAP to interpret hazard scores, showing risk drivers like rainfall, pore pressure, or slope angle. To handle the scarcity of real world data, we integrate synthetic data as well. Importantly, we also introduce a low cost hardware prototype that directly provides ground data, making the system affordable and practical. Here is our prototype. This is a MEM accelerator to detect the vibrations. This is a displacement sensor for slope shifts, soil moisture sensor for subsurface water content, DHT22 sensor for temperature and humidity, 18650 lithium-ion batteries for power, an ESP32 microcontroller for integration and connectivity, along with a buzzer and LED for emergency alerts. When we will actually implement the whole prototype, we will include solar panels so that it is more scalable and sustainable. All of this costs only 1,866 rupees, making it affordable and cost effective even in resource limited settings.
Moving on to the technical approach. Our technical approach starts with the data ingestion part. The data ingestion is done through many sources. The first is the DEM files, which are obtained through ISRO's Bhunidhi website. These DEM files help us calculate slope angle, and roughness. Next, we fetch the weather data like rainfall, temperature, and wind from the NASA Power API. Next, we also take into account geotech signals such as erosion, pore pressure, and displacement. These are simulated now using Richard equations, but in the future, we will also use our custom hardware prototype as discussed earlier. We are using fractal terrain algorithms and time GANs to generate realistic synthetic anomalies. This all data flows into dual branch AI model. The static branch checks terrain susceptibility and the dynamic branch, which is the LSTM branch, checks changing conditions. Together, they generate a hazard index up 24 hours in advance. Our tech stack includes Next.js and Tailwind for the dashboard, Fast API and PostgreSQL for the backend, PyTorch and TensorFlow for modeling, and Sharp explainability, deployed on AWS with Docker and Kubernetes. And last but not the least, we use Twilio to handle real-time alerts. Moving on to the deployed side. This is the deployed side we are talking about. This actually has the admin login showing how the admin will see the dashboard. If you see closely, we have the username password. Also, after selecting the mine, the admin would have to enter the latitude and the longitude of the mine. Also, he has an option to enter the drone data. He can upload drag and drop drone images into this website. So let me log in into the website. Once we click the login page, we have this loader which shows us how the pipeline is moving. Now, for now, this takes a lot less time, but this would actually be computable and give us a real-time dashboard. Now, what you see on the screen is the real-time dashboard which the admins would see. This is the DEM file, and through this we can see actually the zones which we have divided the mine into. The zones, these all zones have different prediction level. So high, low, medium are the three different prediction levels for rockfall. We also see the graphs on the right hand side. These graphs are actually wind, roughness, and slope angle versus the risk of the rockfall. This shows us our features versus the target feature. We also have a bar chart which shows us the sharp explainability. The sharp explainability is actually something of us how we have arrived to the conclusion that there would be a rockfall. This explains us with there is a rockfall's 40% authority into that slope angle, pore pressure, and roughness have significant authority into the prediction of rockfall. Moving on to the next feature, which is the map. This map actually shows us that which zone has a it shows us a personalized humidity, temperature, and rainfall part. We also have one feature where the admin can decide the setting or the threshold for which they want to show that there would be a high prediction of rockfall. When we click into the zones, we will have personalized humidity, temperature, and rainfall at that time, and also the suggestive measures for that zone. We can go back in history or into the present using this toggle feature. Moving on, I'll show you how the admins can generate the alerts and send them to the miners. We have also implemented one more feature, which is that if there is a high risk and admin has not sent any alert, our system will automatically generate and send alert through Twilio. Right now, I'll show you how the admin can send the alerts. By clicking this, by clicking this button, the miner will see the alert here, and this is how the image will be seen, and the alert will be seen.
Moving on to the feasibility, our system is deployment ready, processing large DEMs and sensor data with distributed and edge computing for fast and reliable predictions. Phase training is used that ensures smooth adoption without disrupting the mining workflows. Beyond safety, it boosts productivity, reduces the downtime, and cuts costs. While continuously monitoring of slopes and weather and emission, it supports sustainability and regulation compliant mining. We have a simple dashboard in our system with instant alerts that make it effective even in low resource conditions. Here are the references and the datasets that we used. To conclude, our project is not just an idea. It is a deployable, scalable solution with a single mission in mind: to protect miners and save lives. Thank you.